These are the notes on allotropes, isomers, and cyclochemicals. Allotropes are different forms of the same pure element. An excellent example is we're used to oxygen being O2, that's its most typical form that we find oxygen gas. That's the little peanut that fills our sky that we normally find oxygen in. But oxygen can also make another allotrope, which is called ozone, which is O3. Now this is atypical. We do find a bit of it all around whenever there's combustion, whenever there's hot engines and machinery. And we find a whole bunch of it in the stratosphere in what we call the ozone layer, which winds up protecting us from some of the ultraviolet light from the sun, which is one of the reasons that life on Earth can be unprotected out of the water, in the air, because of that protective ozone layer. It's a good thing that we saved it back in the 80s. So notice that these are both two forms of oxygen made of nothing but oxygen atoms, and yet they have somewhat different properties. One of them will absorb ultraviolet, the other one will transmit it, but they're both gases. The difference between them isn't quite as dramatic as in some other allotropes. Now, ozone is known to have a sweet smell, so if you smell sort of a sweet smell in the air and you're near hot machinery, probably relocate or ventilate the area. A much more dramatic example of allotropes are the allotropes of carbon. Now, carbon, of course, is an essential element for living things, and when it's in its pure state, can occur in several different allotropes. The most typical one is graphite, but it can also occur in a diamond, and it can also occur in buckyballs, which are Buckminster fullerenes is the full name of those guys. So we'll take a look at these different allotropes of carbon. The allotropes of carbon are made of nothing but carbon. They don't contain, other than maybe impurities, any other elements. And yet, simply the arrangement of the carbon can lead to materials that are very, very soft or extremely hard. Either way, just from the arrangement of carbon atoms in the allotrope. The most common allotrope of carbon that you're going to find when you find carbon just lying around is going to be graphite. Graphite is made up of hexagonally arranged carbon sheets, layers of carbon that extend two-dimensionally on and on and on. But you don't just find one layer, you find them stacked layer upon layer upon layer. Now, within the layer, within the two-dimensional surface or plane, the carbon are very well connected with many, many covalent bonds. However, the connection between the layers is very tenuous, very, very minimal. So that causes graphite to be one of the softest of all the minerals. That is why you can take a pencil, which is made of graphite. It's never been made of lead, even though lead is in the carbon family, just further down. And you can write on a piece of paper, write on a piece of cellulose, because the layers of the graphite will just shear right off, slide right off one another with very minimal force applied. So that is why graphite is very good for writing on surfaces, because it is made of layers and layers and layers of hexagonally arranged carbon sheets. And the word graphite actually means the writing mineral, essentially, the mineral that writes. Graphite. Just don't write graffiti with graphite. Think about it. It was shown recently in the past decade or so that you can find special properties if you isolate just one layer of the graphite. So technically that now has a new allotrope applied to it when you only have a single layer of the graphite, and that is called graphene. So graphene is essentially graphite, but deconstructed into a single layer. And I believe they originally did this with a piece of Scotch tape applied to the end of a pencil. Amazing. Then you've got diamond. Diamond is still made of only carbon, and yet the arrangement is much, much different. It's much more three-dimensional. The carbon are connected with each other in every single direction. And so you wind up with sort of a cubic shape. Depending on how you look at it, you could see it as sort of a block, like a cube. Maybe you can't see it here. But if I add the cubic structure, there you go. You can sort of see that it's very, very strongly connected in every possible direction. Well, that is what makes diamond the hardest of all the minerals, all the naturally occurring minerals. Now, another way to look at a diamond is to deconstruct it into its tetrahedral form, because remember, carbon makes 4 bonds that are separated as far as they can possibly get from each other. They're pairs of electrons, after all, that repel each other into that 109.5 degree angle, and that makes the tetrahedral form. Now, if you see that little tetrahedron sitting on top, it's kind of easy to understand how it's just sort of an extended tetrahedron. Each of those bottom 3 carbons in that tetrahedron are the top of a new tetrahedron. And if you keep extending that on and on, what you find is sort of a giant tetrahedral structure, which is another way of viewing a diamond structure. It really depends on your perspective and sort of the angle that you're looking at it. But that explains why diamond is so hard, because it's like a super tetrahedron. Now, if you build a model of diamond, one problem you run into is that eventually you're going to reach the end. And at the end, well, what do? Because you got all these leftover unbonded electrons sticking out. And that is true. So even though a diamond is purported to be 100% carbon, what you actually find is a dirty surface. I guess that's diamond's dirty little secret, that no matter what you're going to do, in order to satisfy the octet of the surface carbons, you got to have something else there, something other than carbon. Therefore, it is truly impossible to completely clean the surface of a diamond. Diamonds are always dirty, but just on the surface, just a very thin layer to satisfy the octets of those surface carbon. Now, this is not as big of a problem as it might sound, because you can imagine this could go on and on and on for quintillions, sextillions. Hypothetically, there is no limit to the size of a diamond other than the pressure generated internally. So you could maybe have a diamond the size of an asteroid. I don't know if it could get as big as a planet. The internal pressure would probably have a problem there. But you could get a giant diamond, hypothetically, if the conditions were right for its formation. So making a diamond model is notoriously tricky. It's one of the trickier models to build because you have to sort of force them to line up correctly. So I'm showing it from several different angles here, but in practice, actually making it can be a little bit tricky. Then we have the allotrope of carbon that is even harder than a diamond. Now you might say, wait, didn't you say that the diamond was the hardest naturally occurring mineral? Yes, but the buckyball initially was not thought to be naturally occurring. It was a synthetic mineral. Now, there is some evidence, people now believe that it is possible that buckyballs might form naturally here and there. But at this point, that hasn't been substantiated. So at this point, we'll still call it a synthetic mineral made of 60 carbons that are interlocked together in a form that's very much like a soccer ball. Now, this structure is called a Buckminster fullerene, named after the great architect, Buckminster Fuller, but for short, almost everybody calls them buckyballs. The structure of a buckyball is very reminiscent of your classic FIFA soccer ball that has alternating pentagons and hexagons. Now, the pentagons are actually all isolated from each other, never coming in contact with another pentagon, a five-sided shape. See the black shapes on the soccer ball. Surrounded by hexagons, which are not so great. They're actually a little bit lopsided. They get short, long, short, long, short, long patterns. So that is very, very much like what we see in a buckyball. What you've got are single bonds, which are longer, and double bonds, which are shorter. The pentagons are entirely made of single bonds. The carbon around the pentagon are entirely single bonded to each other. But as you go around the hexagons, it alternates between single bonds and double bonds. The double bonds, notice, are the ones found in between two of the hexagons. If it's a bond between a pentagon and a hexagon, it is always a single bond. So this is very much like the structure of a geodesic dome designed by Buckminster Fuller and in this type of soccer ball. Not the kind made up of all those triangles, but the classic kind made up of the black pentagons and the white hexagons. Because of this structure, it is a very, very hard material. If you make a model of a Buckminster Fullerene, of a buckyball with 60 carbons, what you find is if you look through any one of the pentagons with the pointy side, like let's say pointed up, you will see directly on the opposite side another pentagon with the pointy side pointed down. That's one way to check that it has been constructed correctly. This will work with any of the pentagons. Okay, you can also find patterns for the hexagons, but they're a little harder to see, and it'll bounce like a ball. It's a really cool model to make. Sometimes I have students make it for extra credit after we finish the organic chemistry section. Okay, it takes at least about 20 minutes just to build it. Even if you know exactly how it's laid out, you have to be careful constructing it, and it takes about 15 to 20 minutes minimum. So these are the allotropes of carbon: graphite in a pencil, the writing mineral, very, very soft, layers and layers and layers of hexagonally arranged carbon. One of them would be graphene. Then there are diamonds, which are blocky carbon, arranged three-dimensionally, very, very hard, the hardest naturally occurring mineral. And the buckyball, which is even harder, but only 60 carbons. Now keep in mind, I'm only showing a small segment of diamond there, but diamond goes on and on and on to the point where you can actually see it. Think about that diamond right there. Can't you see it? Isn't it macroscopic on any diamond ring? That is a macroscopic molecule, which is kind of amazing if you think about it. A molecule that grows so big you can see it with your naked eye. Now, a buckyball is not like that. Even though I'm showing a larger segment of it here, I'm showing all of it, 60 carbons, it is still a very, very microscopic molecule. However, hypothetically, if you could construct the equipment correctly, you could fire little buckyballs, okay, out of a little cannon, microscopic cannon, and smash apart a diamond. So the buckyball would be harder than the diamond. However, it is a microscopic molecule, whereas diamonds can grow enormous. Like I said, maybe even the size of an asteroid, which really takes the microscopic up to the macroscopic in a tremendous way, in a way we really don't usually see. A macroscopic molecule. So I sometimes have students build buckyballs and diamonds for extra credit after we finish the organic chemistry section. And surprisingly, the buckyball winds up being the one that is much more successfully built. it's actually easier to construct it because it sort of forces itself into that shape. It pulls itself around into that soccer ball. Whereas the diamond, with any misalignments, doesn't work out right. You have to be very, very careful to line up all of those bonds correctly in order to get a successful amount of diamond. And the amount of diamond that I accept for extra credit is a diamond containing 60 carbons, proportional to the size of a buckyball. But it's a little tricky to build it because getting all those little tetrahedra lined up correctly is a pain. Good luck. Now we have isomers. What's an isomer? Well, you can have C3H7OH, and that's propanol. And normally, the functional group for propanol, hydroxide, is attached on the end of the chain to the first propanol on the chain, which is called 1-propanol. So you can think of this as your regular, typical form of propanol or propyl alcohol. But what if that hydroxide is not attached to the end carbon? Now, think about it. If it was attached on the other end, well, it's the same thing. You just swing it around, right? But what if it was attached to the carbon in the middle? So now we have C3H7OH. It's still propanol, it's still propyl alcohol, but there's something different about it. The functional group, the hydroxide, is attached to the second carbon. So we call it 2-propanol. Now that could be the second carbon from either end in this case, but usually we count from whichever end it's closer to. Just in this case, there's no difference which end you start with. This is called an isomer. It has the same molar mass, it has the same chemical formula, and yet it has a different chemical structure, molecular structure, when you look at the Lewis structure. And it can have slightly different properties. This is actually the form that we use in alcohol pads when we have isopropyl alcohol. So isopropyl alcohol is an isomer of propanol, so it's a very good name. And an isomer is essentially the same chemical with a different structure. Usually it's because the functional group is attached to a different carbon in the chain. So they're equal in many ways. Molar mass is equal, chemical formula is equal, and yet the Lewis structure differs. That's what an isomer is. And we have this with every single organic chemical that has a functional group attached. You can have a different isomer of it. So that's what an isomer is. Now we come to the cyclochemicals. Now, a cyclochemical is a chemical that makes a circle from the Greek word kuklos for circle. And obviously, this is a circle alkane, right? Cycloalkanes. Remember, the alkanes are the chemicals that all have single bonds. Now, normally, alkanes are saturated, but in this case, saturation means something slightly different because they have as many hydrogen as a circle of this many carbon could contain, which is somewhat less than a linear chain could hold. So you'll see that the formula for cycloalkanes is not the same formula for regular alkanes. So the formula for cycloalkanes is CnH2n, which is surprisingly unsaturated, which is funny because alkanes normally are saturated. The reason it's not saturated is because it contains a loop. The carbon come back together with themselves, and so some of the bonds that would normally hold hydrogen are used to connect the carbon into that loop. You'll see what I mean when you see the models. Notice how the formula for the cycloalkanes is the same formula for the alkenes. Now, that can cause some confusion. So you could actually have the same exact chemical formula, but it could have more than one possible structure depending on if it's a cyclochemical or not. So you have to make sure to give some kind of notation about the structure. Otherwise, you're going to wind up with two possible variations. the cycloalkane version or the alkene version. Here we have the very first cycloalkane, cyclopropane. Now, why isn't there a cyclomethane or a cycloethane? Well, that's because you can't make a circle with one carbon. You also can't make a circle with two carbon. So the smallest sort of loop you can make, I guess it's not really a circle, more of a triangle, is with 3. So the smallest number that you ever see in a cyclochemical is 3 carbons. And then because it's CnH2n, it's C3H6. So you can sort of see why. It's a little triangle of carbon. Each carbon has 2 other hydrogen attached. And you can see why the octet is satisfied for all the carbons. Let's move on. The next cycloalkane is cyclobutane, which of course looks kind of like a square of carbon. Not exactly a square because it's not coplanar, but it's C4H8 because CnH2n. And it looks something like this. Here's the model. Okay, so notice that still every carbon has 2 hydrogen attached, in addition to be attached to the 2 neighboring carbon. So you can sort of see why this has fewer hydrogen than if the carbon were all in a chain, like a snake that wasn't connected in a loop, because 2 of those positions have been transformed into links between the carbon where they could otherwise hold more hydrogen, therefore unsaturated. The next one, no surprise, is cyclopentane, which is sort of like a pentagon of carbon, but not exactly because it's not coplanar. And it looks something like this. I kind of like this one. This one looks pretty cool. And it's C5H10, no surprise. Then you get to cyclohexane. Interesting, right? It's like a hexagon of carbon. Again, not a perfect hexagon. And there's 2 hydrogen attached to each carbon. And it looks something like this. Here's the model. Now, this reminds me of another chemical that we've seen that has 6 carbons, but only 6 hydrogen, that we call benzene. So cyclohexane is not the same thing as benzene, although if you just look at the carbon, take a good look at the carbon, those are the same. Now watch. Benzene is C6H6. It's a very characteristic form of carbon with hydrogen attached, a hydrocarbon, that is found in the aromatic chemicals. It's a very common structure. The model looks something like this. Now notice the double bonds. Well, because double bonds can't really exist between 2 carbon and not between the next 2 carbon, they're in resonance. So it's really something in between a double and a single bond alternating back and forth. But notice that each carbon, because of those double bonds, only has 1 hydrogen attached, which is very different than what we saw in cyclohexane. So let's see the difference for comparison. Starting with cyclohexane, let's transition it to benzene. Watch. Now notice that each carbon has lost 1 hydrogen because it needs to make a double bond with one of the neighboring carbons. But then, of course, those are resonating back and forth and back and forth. Now let's transition back, watch again, to cyclohexane. So it has twice as many hydrogen, but only single bonds. So in other words, benzene is not a cycloalkene. Got it? Now we come to cycloalkenes. Cycloalkenes are actually chemicals that are unsaturated, but not just for one reason, because it comes back in a loop. That's one reason to be unsaturated, but for another reason, like the regular alkenes, because they contain a multiple bond, a double bond. So essentially, these have a different formula, as you would expect, and guess what it's going to be? They've lost 2 more hydrogen, so guess what it's going to be? It's going to be CnH2n minus 2 for these cycloalkenes, which is actually the formula for the regular alkynes. So it's interesting that we see some of these exact same chemical formulae repeat for different classes of chemicals depending on if they're linear or snake-like or if they connect in a circle. Of course, this is unsaturated, like I said, for two reasons. Because it's a circle and because it has a double bond. Here's the first one, cyclopropene. Now, cyclopropene is kind of a triangle, but not a equilateral triangle, more of an isosceles sort of triangle of the carbon. And then it's C3H4. Oh, that's because it's 2N minus 2. So double 3, that's 6, minus 2, you're back to 4. C3H4. Does that make sense? And you can sort of see why it is unsaturated. It's missing quite a few of the possible hydrogen that many carbon could hold. Then we've got cyclobutene, same deal. It's almost a square, more like a trapezoid of carbon, and it's C4H6 because double 4, you get 8, minus 2, back to 6. C4H6. There we go. Next one. Cyclopentene. Need I say more? C5H8, because you double 5, you get 10, minus 2, back to 8. And it would be the same chemical formula. You wouldn't know by looking at that formula that it wasn't an alkyne unless you knew that it had a circular structure. It was a cyclochemical. So that's why you've always got to make sure to note if it's a cyclochemical as opposed to a more linear snake-like carbon chain. And the last one we're going to look at is cyclohexene, which of course, same thing goes. It's like a hexagon, but not a perfect hexagon. And it's C6H10, unsaturated. Now, let us come to the cycloalkynes, which have a formula CnH2n minus 4, obviously very unsaturated. This is a formula we just haven't seen before. It's not the same formula as the regular alkynes, the linear alkynes. It's got 2 fewer hydrogen, so it's really missing out on a total of 6 potential hydrogen that it could have had if it was saturated. Wow. And of course, it's unsaturated for 2 reasons. It comes around in a circle, of course. It's a cyclochemical. And it's got a triple bond. That's the other reason. So this is very, very unsaturated, a formula we haven't seen before, CnH2n minus 4. So let's see some examples. So here we have cyclopropyne, and it's C3H2. There's actually fewer hydrogen than there are carbon. Interesting, right? So why is that? Because double 3, and you get to 6, and then minus 4, you're back to 2. C3H2, cyclopropyne. Let's see the next one. Cyclobutyne, C4H4. The hydrogen and carbon happen to be equal here. And it's not exactly, I guess it's a trapezoid again, but double 4, you get 8, minus 4, back to 4, C4H4. So the carbon and the hydrogen happen to be equal in this particular formula, kind of like we have with ethyne, okay, the regular old ethyne. But here it happens with cyclobutyne. Then we have cyclopentine, which kind of, I don't know, that's a messed up pentagon. C5H6, the hydrogen just barely outnumber the carbon, severely unsaturated. It's a strange looking chemical, to say the least. And let's finish off the cycloalkynes with cyclohexyne, like we've been doing, with a prefix of hex, meaning 6, C6H8, so double 6 you get 12, minus 4 back to 8, C6H8. And yeah, it's kind of an odd looking one. And remember that triple bond is significantly shorter than the single bonds. It's significantly shorter. It's about 78% as long as the single bonds, dramatically shorter. So cyclochemicals obviously come up inside other organic chemicals, And you can sort of see cyclochemicals, although not entirely composed of carbon, in many everyday well-known molecules. One example is caffeine. Okay, caffeine isn't exactly a circle of carbon. It does contain nitrogen, but you can sort of see how it's a modified version of one. It does have that sort of hexagonal pattern within it, as well as a pentagonal pattern within it. Other examples of chemicals that look like cyclochemicals but aren't quite are the nucleotides from DNA. So we've got adenine, looks sort of like a hexagon. Thymine also looks sort of like a hexagon. Guanine, again, same thing. Not exactly because of the nitrogen. And cytosine. So essentially, you can sort of see how these could have been constructed out of cyclochemicals. At least the idea of cyclochemicals is involved in their structure. But then, of course, it quickly gets out of hand like it does in biology. When you start combining these pairs together, and then, of course, into the strands of DNA, and it just gets all out of control. And very quickly, you've got living organisms evolving and mutating and so on. So that gets into the realm of biology. But it's interesting to see how cyclochemicals, if you look closely at this, you can see some of those little hexagonal loops are involved here. So that is the end of the notes on allotropes, isomers, and cyclochemicals. Hopefully that initiated you into a little bit more of the wider world of organic chemistry. Thank you. Bye.